Number 6 is another example of a rational equation. So we're going to take our 2x squared minus x minus 3, factor the numerator to find the zeros, our 2x cubed minus 7x squared plus 6x, and factor it to find our vertical asymptote. So in the numerator, we can factor that binomial or that trinomial into two binomials. It's 2x and x. Signs have to be different, plus and minus. We want to make sure that we end up with a negative 1, so at minus 3 plus 1. That way your outside inside give you a negative 1. On the bottom, the first thing I can do is I can factor out an x. I'm going to be left with 2x squared minus 7x, then plus 6. And we'll factor that again a second time. So that's x times trinomial factor the binomial. The only factors of 2 that we could use are 2x and x. Our factors of 6 that we want to use are minus 3 and 2, so minus 3 and a minus 2. So I don't know if I have those in the right spot yet. I got to double check. That's a negative 6, negative 2, that's a negative 8. So I don't have those in the right spot, so I'm going to switch them around. I'm going to put the 3 there and the 2 here, and I'm going to double check. That's a negative 4, negative 3, that's a negative 7. Okay, so now I have it factored correctly. And I can start plugging in the information I need. What I need, first of all, is the domain. And the domain is what would make our division by 0. So here's a problem, 3 different locations. And one of the locations that we'd have would be a hole, but it's still part of our domain restriction. We do not want x to equal a 0. We do not want to equal a 3 halves. And we do not want to equal a 2. So if we use that interval notation that we were using, we're going to go from negative infinity up to 0. We're going to union it with 0 to 3 halves. We're going to union that with 3 halves. Try that again. 3 halves to 2. And then we got to union that, so I'm going to run out of room, so we'll union, and then it's going to be 2 to infinity. So with that one, it's a lot easier to say what you can't use rather than writing your interval notation, but just keeping it consistent, that's how I would end up writing that. Vertical asymptotes, so where our denominator would equal 0, so we have vertical asymptotes at x equals 0, again at x equals 3 halves, and then finally when x is a 2. So we have 3 lines. Check that. I'm going to back that up a little bit. I have an error in that. I want to come back and make sure that I locate that hole first. We had a hole rather than a vertical asymptote. Anytime you have the same factor on the top and the bottom, that's going to be a hole. So it's still part of my limitation of the domain. It won't change that, but it will change the fact of what I was writing down there for the vertical asymptotes. It'll be 2 vertical asymptotes, one at x equals 0 and one at x equals 2. And I'm going to come over here and plug in that hole right away. We're going to have a hole when x is a positive 3 halves. And then we'll look at our horizontal asymptote. In order to determine our horizontal asymptote, it's a matter of degree. And going back to our original, it's a 2nd degree over a 3rd degree. So anytime the denominator has a larger degree than the bottom, it will always have a horizontal asymptote at y equals 0. That fraction will always approach 0. So there is no oblique asymptote, which means we could look for the x-intercepts. The only thing that's left is when x is a negative 1, so our x-intercept is negative 1, 0. And finally, the y-intercept. The y-intercept is if we plug in 0 in for your x's, then that's going to make it undefined, so that means it cannot touch the y-intercept. So there's the information that I requested on this next rational equation.